Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to welcome Sven here from Harvard. He's in the Daily Parts Group, and he's also come to Harvard via Massachusetts, UMass, and Stuyvesant as well. So welcome, Sven, and over to you. You want to talk on hidden market.
Thank you very much, and thanks a lot for having me. I'll be talking about a piece of work from my PhD thesis on hidden markets, and in particular I want to talk about the question how to design efficient but simple electronic markets. And I want to start talking about these markets that we are all used to, like Amazon or eBay, which make it very simple to buy or sell goods on electronic markets. But I argue that in the future, lots of new technologies will emerge that enable new markets. For example, we can already answer or ask questions on the internet and be paid for that or pay for that. When you're driving your car, you might soon have to pay a toll that depends on the current traffic on the road that you're driving on. Google One Pass, which has just been introduced, will enable all new kinds of markets for consuming online content. And soon, when you're consuming electricity, you might have to pay a price for the energy you're using that depends on the current consumption in the submarket that you're in. So these markets can sometimes be pretty complex. Depending on the particular domain, users might have income or expenditures. They might have a budget that they spend over time. Prices might change. You might trade with other participants of the market. And there might be complicated constraints on these trades. At the same time, the systems that I'm thinking about will mainly consist of non-expert users, or it might be too costly to become an expert in that particular domain. And we're thinking of millions of users, which in some domains might not even expect the market to begin with, or they might find money kind of unnatural in that domain. So to summarize, we have all these new complex markets that are emerging in the future with lots of unsophisticated users. And so my research question is, how can we design efficient but simple electronic markets for these particular domains? And I argue that to answer this question, we need a new kind of market design approach where we're trying to hide some of the market's complexities from the user and make the interaction as seamless as possible. And this is what I mean with this term hidden market design. And I want to point out that there are different degrees of hiddenness that we can have. Sometimes we might be able to completely hide a market from its users. Sometimes we might only be able to hide some of the complexities of the market, and sometimes we might only be able to hide a certain element of the market or of the complexity. So I argue that there are three important components of hidden market design. The first one is the user interface design. The user interface constrains the kinds of markets that we can effectively design, and it also defines how a user expresses his preferences in a particular application. At the same time, via the user interface design, we define the amount of cognitive load we are willing to put on the user, which is very important given that we're dealing with boundedly rational users that have a value for time and outside options. On the other side, we have the market design, where by specifying the rules of the market, we are defining the market's incentives and whether the users will have a need for strategic interactions, and we will determine the economic efficiency, revenue, and fairness properties of the system. So these are kind of the two obvious ones, and then I argue there's a third one which is also kind of important, namely artificial intelligence, which can help to bridge between the two things. On the one side, we can automate and simplify certain decision-making tasks for the users. For example, by using learning algorithms, we can automate certain tasks. And sometimes by, for example, suitably designing proxy agents, we can translate certain parts of interactions between the user interface and the market.
Just a quick question. What's hidden about the market?
I think that will become more clear throughout my talk. But yeah, so different aspects of the market can be hidden. Sometimes we are hiding the fact that there is a market. Sometimes we're just hiding some of the complexity from the user. So it can mean different things. So this is a different high-level view of how I'm thinking of the task of designing the hidden market user interface. So we might have a very complex underlying market with changing prices and account balances and bundled constraints. And the UI designer's task will be to design a hidden market UI that's kind of wrapped around the complex market, only exposing a simplified interface to the user, to then invoke a particular mental model leading to a user action, which in turn still influences the underlying potentially complex market. And the trade-off will generally be between simplifying the UI further, but without losing too much of the potential economic benefits of the market in the first place. So there's some related work that I want to mention. One is by Paul Milgram on simplified mechanism design. So this is very similar in spirit in that Milgram shows that by eliminating certain actions from sponsored search auctions, in this case, we can eliminate certain undesirable equilibria from the resulting game. So it is similar in spirit in that, as the same as in our domain, he shows that by simplifying the market mechanism, we can actually increase the market's efficiency. It's quite different in that in our work I'm not concerned about selecting certain equilibria from the game, but I'm concerned about the complexity of the user interface that we're exposing to our participants. Some other work I want to mention more on the UI side is by C, Crowd, Hudson, and Weber on the question of can markets help they study a particular domain, namely synchronous communication, essentially chat protocols, where they show the various complications that are involved in introducing a market into a domain where previously there wasn't a market, and to what degree that can help and to what degree that can be challenging to users. And then there's a third application I want to mention by Guel, Panak, Reeves, and Yu, who introduced UPick, which is a combinatorial sports prediction market. And it's an application on Facebook which lets users make bets on a combinatorial market simply by having two sliders that they can move left and right to specify their part of a probability distribution that they want to bet on. And that's also very much in line with the hidden market idea in the sense that it's hiding a lot of the underlying complexity from the users but lets them effectively interact with the market. Okay. So here's a brief outline of my talk. After this brief introduction to the general idea of hidden markets, I'm now going to deep dive into a case study that I worked a lot on a hidden peer-to-peer backup market. And I'll show you the market design elements of it, the user interface we developed. I'll talk a little bit about the theory and then the user study that we performed. And then at the end, I'll present a brief overview of some of my other market design projects, and then I'll conclude. So the first question is, why even study peer-to-peer backup? And motivation is pretty easy because the data loss cost in the US in 2003 already exceeded $18.2 billion. And the main reason for this is that traditional backup solutions are simply too cumbersome. Backing up your stuff on DVDs or CDs just is not feasible for most users. So fortunately, we have online backup where we can easily send our data to a data center, which is easy, but which still incurs lots of costs on the data center side.
So then is that figure based on 18 billion, is that from industry or is that?
It's combined industry and personal usage, yeah. So yeah, I think the bigger cost drivers come from industry when you have lots of work that gets lost by stolen laptops or burned down laptops, whatever. So to address the expensive data center point, one idea is to use peer-to-peer backup, where each user that is consuming some of the backup service also has to provide some of his resources in return. And the resources that we need are backup space, upload and download bandwidth, as well as online time. And the savings here come from the fact that we're using otherwise idle resources and decentralization to save various kinds of costs. The costs that we're saving are storage costs, energy costs, maintenance costs, and peak bandwidth costs. So this is a great idea. However, there's still one problem, namely, this can be inefficient if we force every user to supply the same kinds of resources. Yes, you have a question.
So when you say you save storage, you mean you save storage for the service provider? Because overall the storage is the same, right?
Right. Overall, the storage is actually will actually turn out to be greater because you need certain amount of replication to be safe. However, actually a study conducted by Microsoft, I believe in 2007 or 8, showed that more than 50% of Windows users have more than half their hard disk free. So that's a lot of idle storage that can be used for backup without losing too much value for its customers. Yes.
Do ordinary people understand the concept of peer-to-peer? Would that not create some more problems?
I believe that obviously ordinary people don't understand the details of peer-to-peer, in particular of the peer-to-peer backup market. And that was one of the challenges that we had to address in developing this design. And so I'll show you how we address that, and then I'll show you some results from the user study in what respect users were able to cope with that. So the point I want to dwell on is that if you design this naively, you get lots of inefficiencies if you force every user to supply resources in the same ratios. And we want to maximize efficiency by using a market in this domain. So to explain this point in a little more detail, let's consider two consumers. A consumer A, who has a very large hard disk and a slow internet connection, and consumer B, who has a small hard disk but a fast internet connection. If we didn't have a market, then users A and B would have to provide the same amount of resources in return for consuming the backup service. By using a market, we can let them supply different ratios of resources. We can let user A provide lots of space and very little bandwidth, and user B in return can provide lots of bandwidth and little space. And in that sense, we are maximizing efficiency, which in this domain means we're going to use those resources that the particular users value least, so the most willing to give those resources up. The current state of these systems is that on this side, there's already a real-world system that's deployed in practice. It's called Voila.com, and you can use it to back up your data. And on this side, this was a Microsoft research project which started out at Microsoft Live Labs in 2008 that I got involved in. So we had lots of researchers and programmers involved in the networking and encryption part of it, and I came and joined the team to develop and design the underlying market of the system, and which I designed and implemented and then tested. And that's what's going to be the talk about. So here's a high-level view of this system. At different points in time, a particular user of the system is either a consumer or a supplier of resources. As a consumer, we take a source file that he wants to back up, which is then split into many fragments and stored across many different suppliers. Each supplier has to supply some of the storage space, upload bandwidth, download bandwidth, and online time to participate in the system. Whenever a consumer backs up one of his files, he has to pay a certain amount of credits to the server, who then in return takes that credit and spreads it across the suppliers that are involved in that particular interaction.
There's a one server.
There is in the...
It might be replicated, but notionally there's one.
Yes, notionally there's one server. It's a very lightweight interaction that none of the actual data is stored on the server, only some metadata is stored there, and the server is used to essentially coordinate and monitor the transactions that are going on. Monitor to a very limited degree, that all depends on reporting. Okay. So the first concern people have, did you have a question? Or no? The first concern that people have when they hear about peer-to-peer backup is security and safety. So, of course, we want to design the system so that it's reliable and has the same or higher reliability guarantees compared to centralized data centers. And that's often measured in terms of instantaneous file availability, where a typical goal is something like 99.999%. So, to achieve security and safety, what we do is, before your file leaves your computer, it's first encrypted with a private key. And then it's encoded using an erasure coding algorithm. And then it's split into many small file pieces which are distributed over hundreds of peers. And the erasure coding algorithm has the following property, that after the file is encoded, if we generated 100 pieces, then let's assume the original file consisted of 50 pieces, and we generate 100 encoded pieces, and then we distribute the 100 pieces across 100 peers. Then it has the property that to reconstruct the file, we don't need a specific set of 50 pieces, but any 50 out of the 100 pieces will be enough to reconstruct the file. So this is the reason why doing something like peer-to-peer backup is even economically feasible without having huge overhead. So to give you a rough comparison, if we assume that every peer is only online 12 hours a day, then if you wanted to achieve this kind of reliability, you would have to replicate the file 17 times to make sure, I can always access my file with that probability. By using erasure coding, I only have an overhead of factor 3 instead of 17. So this is why this is even makes sense. So now I want to show you a quick demo of what the system looks like in practice. So I'm actually running the server and the client on my computer. And I can start a new backup, which I'll call MSR. And I'll select one of my folders to do the backup. And then I'll click on Begin. And it's compressing the file, and then it's encoding and encrypting it. But this was even faster than you could see. And now it's already streaming it to the peers. I'm also running 50 peers on my laptop, and every time you see one of these lights flashing, a new fragment just was sent to one of these peers, which is now storing them. And when it stops flashing, then it's done. So we just backed up a 5 megabit file, and it could have been into any, so this is all done via TCP/IP. These 50 peers could have been anywhere in the world, and we also tested that. But because I'm not connected to the internet, I didn't want to show this live. So this is what it looks like in practice if a user wanted to back up a new file in a system. He simply gives it a name, selects a folder, and clicks on Go. So the user doesn't really have to know that so this partly answers the first part of your question, doesn't really have to know that this is going to a peer-to-peer backup system or to a centralized server. It just disappears into the cloud, and we guarantee the user essentially the same guarantees as we could with a centralized system. Now let's move on to the challenges of designing the underlying market of this. So far there was no visibility of any kind of market. So for the user interface design, the first challenge is that using money or market at all in this domain is very unnatural for most of our users. And furthermore, the UI must be particularly simple if we're targeting millions of non-sophisticated users that don't want to spend all the effort of becoming an expert in a particular domain. The third challenge is special to our problem or to our application, namely that we have these very strong complementarities between the resources that a particular user has to offer. And the complementarities are such that if Peter only gave me some of his hard disk space to use in the system, but none of his bandwidth, then all of his disk space will be completely useless because I could never send or receive any file fragments from his machine. So his disk space only becomes useful to the system if he also supplies at least some of his bandwidth in a certain ratio that makes it useful. And the other way around. His bandwidth is only useful if he also gives me some disk space. So these complementarities have to be exposed to the users in some way because they're supplying these resources to us.
Isn't that in tension with your earlier remark that it's okay for some users to supply lots of disk space and no bandwidth, and others to supply lots of bandwidth and no disk space? Right.
So there is a certain tension. There's a kind of a minimum and a maximum ratio that they can. So there's some wiggle room, and this wiggle room results from the fact that we have actually two or three reasons why we have that wiggle room. One is there are cold files and hot files. Cold files are stored once and then rarely accessed. Hot files are accessed very often. So these hot files need a lot of bandwidth. So if I store the hot files on the users that are giving me more bandwidth, they can make use more of their bandwidth. The second aspect is we have certain repair and testing operations that are done repeatedly to maintain safety in the system. And these mainly require bandwidth and no storage space. And if I let the users with the lots of bandwidth supply do those operations, I can again use more of their bandwidth and less of their storage space. So by allocating this kind of work to certain peers, I can make more or less use of their various resources. However, there's a minimum and a maximum boundary. Not a user can't just give us 0 of any of the resources. And you will see how we expose that in the user interface in a second. So these are the challenges for the user interface. On the market design side, the first problem is we need to elicit the user's preferences which here means their relative value of the resources they're willing to supply. The second challenge is that here users might be unresponsive. They might not update their settings for a month or so. They might not care about their resources enough, and we have to take that into account when designing the market. And then the most important part is we want to make sure the system is always safe, in the sense that we always have enough supply to guarantee that we can satisfy any kind of incoming demand into the system. We can never have the situation that a user wants to back up his files and we tell him, sorry, not now, try again tomorrow. So the contribution that we make is that we are designing this, what I call hidden peer-to-peer backup market. Very important in this design process was that we designed the market and the user interface in concert and not one after the other, such that we could guarantee that the resulting market is efficient, but the UI is still simple enough to use, and such that we are hiding the market complexities. To address the safety of the system, I performed this theoretical analysis where we show that in the market's equilibrium, the system safety will be maximal. I will show you how and when we can achieve this equilibrium and how robust it is to any kind of irrational or adversarial behavior. And then we studied the usability of the system via an exploratory user study to figure out if the system is actually simple enough to use and whether we can achieve the efficient allocations in the market.
When you said the market is efficient, your first bullet,
Yep.
the market is efficient, and then you said safety in your second main bullet.
Yep.
Is that the same thing?
I
Is it?
It
I suppose I'm trying to connect the first summary.
Yeah. On a normative level, it's a slightly different thing, because you can make the system safe essentially by forcing all the users to supply certain resources, otherwise you would kick them out. And efficiency means you want to give each user the maximum amount of freedom in supplying those resources that they're most willing to give up. So it's a slightly different.
So your really requirements are safe, efficient, and simple.
Yes. Interestingly enough, we show that under certain assumptions, actually safety and efficiency, once you consider the hard constraints on the maximum boundaries for the wiggle room that we're giving users, then to some degree safety and efficiency actually falls together nicely. I'll show you that in a second. So on the macroeconomic design, there's only a few things I want to mention. Namely, on the server, we are storing an account balance for every user who's registered in the system. And every user starts with a balance of 0, and then we allow the user to take on a bounded deficit. And once he reaches that deficit, we don't allow him to perform any more backup operations before his account balance goes positive again. The design implication from this account balance concept is that the user doesn't have to monitor his account balance over time, because the server simply assigns the work to those users that are currently most negative in terms of their account balance, such that their balance is driven back to 0. And so if a user is online sufficiently long, his account balance will always be somewhere close to 0. On the microeconomic design side, the first thing we have to notice is that we have a market where we have production and consumption happening, but the server is actually the only producer in the system, in the sense that the server is the one who takes these unreliable resources from different peers and bundles them together and sells them as a reliable backup service. And so this allows us to model this market as an exchange economy, which makes a lot of the things much easier for us. And now we can define one price for each of the input resources that we're using in this exchange economy. And we will assume that the prices are updated once a day by the server. And the user's task will be to react to these price changes, which will mean to adjust their supply and the demand in this market, obeying these complementarity constraints that I mentioned a second ago. And if you think, well, this sounds pretty complicated for most of the users of a backup system, then I agree that it is. And that's what we wanted to hide from the user to a large degree. So next I want to show you what this user interface actually looks like if the user wants to interact with the market. So let me see if this works. If the user clicks on the settings button, this is the window that opens, and this is essentially the user's way of interacting with the market. On the left side of this window, the user sees his currently available online backup space. So here the user sees that currently he has backed up 17.929 gigabytes, and he still has another 11.49 gigabytes of free online backup space. On the right side, the user sees which kind of resources he's giving up in return for this. He sees that his disk space, upload bandwidth, and download bandwidth have these values, and then his current online time is 12 hours a day. And if the user wants to change any of these settings, he can move one of these sliders to the left or right and change kind of the maximum he's willing to give up. To change this number, he would just have to leave his computer on more or fewer hours a day. So now if the user wants to change something, he can either move this bar chart on the left to move this up and down to specify how much he's willing to give up in return, how much online backup space he needs, and what you see is that we are automatically moving the sliders such that the user will automatically be balanced over time. So if the user wants to have more online backup space, we're automatically increasing the sliders so that he's providing more in return as well. Of course, the user can also move the sliders on the right side individually kind of to fine-tune the settings for him, how much he's willing to give up in return. So this is the way how the user can express his preferences. One user might be willing to give up lots of his space because he doesn't need it, but he really, really needs his upload bandwidth because he's doing video conferencing or something like this. Another user might be happy to give up lots of his upload bandwidth, but might not be willing to give up lots of his space in return. So different users can specify different preferences depending on their needs and their endowment of resources.
A good question about the bandwidth. So the maximum, is the bandwidth in any sense measured? So for example, you've got maximum figures on the right there.
Right.
And
So
the user might not have a clue what, and it might change in time what they can actually upload. Are you getting those, coding the tool for those or using statistics to get those?
So at the moment, I just hard-coded these two numbers in. The idea for the eventual product was that you would do a speed test at the install time to figure out, okay, what's the maximum bandwidth that this user has, and then these would be the numbers on the left and right. Yeah. But that's kind of a product decision how to get these numbers. Yeah. So I told you that that there are these, yes, question.
So if you have, like in this example, you have 18 gigabyte use, can you just drive everything on the left to 0 because you want to get 18 gigabytes for free without giving up any space and any bandwidth?
Yep. So I'll show you exactly that now. So if the user says, well, I don't really want to give you any of my disk space, then he could reduce the slider all the way to 0, and then we'll show him, sorry, for that you'll get 0 gigabytes of free space in return. And what will also happen, I mean, now he's still using these 17.29 gigabytes. What will happen is now, if the user clicks on OK, the user's account balance, will start to go negative because he has to keep paying for this, but we can't pay him for any of his resources. So if he changes this back tomorrow, nothing bad happens. If he leaves it like this for a while, very soon we'll send him an email and say, sorry, you've reached your maximum deficit level. If you don't keep increasing your supply of your resources, and just open your settings window and move the sliders, then we will have to start deleting your files. And the policy decision from the product group was something like, okay, we'll give you a grace period of 4 weeks, and if you haven't done anything in 4 weeks, at some point we have to start deleting your files. It's essentially similar to if you're leasing a car and you're not paying anything for 2 months, at some point we'll come and take the car back. So, but let me dwell on this point a little more. So if the user moves the slider all the way to the left, what happens is, actually, is there a way to turn off the light for a second because you can't really see the colors? Just for a moment. Good, yeah. So the user gets 0 in return because he's not supplying enough space to make any use of the other 2 resources. So if the user gives more of these resources, then at some point we will give him more online backup space in return. What you see is that these sliders have different color coding, namely blue and gray, where blue means that this resource is useful to give up and gray means it's not useful to give up. So what this means is if I move my slider within the blue region, then the bar chart on the left is responsive. But once I leave the blue region, I get this little pop-up which tells me that to give more useful upload bandwidth, you first need to give more space or download bandwidth. So I've moved into an area where giving more bandwidth beyond this point is no longer useful to the system. So I've exceeded this boundary or this wiggle room. And now the user has to first increase how much space he's providing to make use of that bandwidth again. So sorry, I'm actually at the limit here. So let me show how this looks here. So here now you see, okay, I'm reaching the limit, and if I want to make use of this bandwidth supply here, the user has to supply more of his space, and then you can see that the blue bar starts growing again, and now the user can also give more of his bandwidth before reaching the limit here. This is kind of the way how we're exposing the complementarities between the resources to the user in a visual way. So the user can never set his sliders in a way that will violate any of the flow balance constraints.
So if I reduce my the space, my supplied space, what will happen with the stored files on my drive to back up files?
So what we wouldn't do is immediately start erasing all of the files, but we would essentially mark them as erasable, such that when if you move your slider all the way to the left and click OK, and then again all the way to the right, that we wouldn't have to store another 100 gigabytes of files again. But they would essentially be marked as erasable so that it shows up as free disk space. So that's the idea behind it. The last point I want to show is the pricing aspect. If I told you that the resources have different prices that change over time, but we are not displaying any dollar signs. And the way the user can figure out the current prices of the different resources is in the following way. If the user moves this slider here a little bit, then we see that the bar chart on the left only moves up and down a little bit as well. However, if the user moves this slider a little bit, then we see that the bar chart moves up and down a lot. So what this tells the user is that this resource is currently very expensive relative to this resource. So by giving a little bit more of that resource, he gets a lot more bangs for his buck than supplying space. Yes?
I know you've already mentioned this to some extent, but it's still unclear. Why is this controlling the amount of free space rather than the space available for backup?
Oh, okay. It's actually, when I implement this, I also thought about it effectively is controlling all of the available space to the user. I mean, you could also have a bar chart. As you're moving the slider, you could also have this go all the way down to 0 and just start using a different color coding here or so. I mean, essentially, it's controlling how much you can afford. It's just, the policy is when you move the slider, we won't start deleting your files immediately. You have this grace period to keep supplying again to come into the positive area again. So, but you're right, it's essentially controlling your whole income that you can use to spend for online backup space.
But over time, you're either gaining credit or losing credit.
Sorry?
Over time, you're either gaining credit or losing credit. The system is trying to drive it towards 0.
Right, exactly, yeah.
And so, you get to see your credit balance?
No, you don't get to see your credit balance, which was a design decision we made on purpose, so that you don't have to monitor how your account balance goes up and down. Instead, the idea is that if you set your sliders like this, and your user behavior profile remains similar to the last 100 days, then you will be able to maintain in good standing over time. So essentially, we are measuring how often you're online over time, and then we're telling you, based on how often we see you, this is how you have to set your sliders to afford this kind of a consumption. Yes?
Isn't the user going to be interested in equilibrium conditions? Like they just want to sort of set this up and then say, I'm going to be able to have this much stored over time.
Forever.
Like you seem to be talking about something more dynamic, which is that I can have this much stored today, but tomorrow you might send me an email.
So that's a good point. And so of course ideally I'd like this world where I can offer you this contract once and then you're set for your lifetime. But remember that this is, I'm making a contract about supplying you with this service essentially forever going forward, right? And nowhere in the world can you make a contract about this, which will give you an infinite lifetime guaranteed to buy this contract at this price. You know, prices keep, perhaps you'll be able to buy a contract that says, okay, for this price you'll get this for a year, but then we have to renegotiate prices. Similarly here, because prices on the supply side can change, because suppliers can change how much they are willing to supply, what you have to pay on the demand side is also changing. So if the user sets his sliders today, he might have 7.23 gigabytes of free space. If he comes back a month later or a day later, this might be 6 gigabytes or 8 gigabytes. So it might change a little bit, and this might be confusing at first. But the idea is, as long as this only changes from 6 to 8 gigabits of free space, there's nothing bad that happens, because it's not affecting you at all. The only time something it might affect you is when it changes from 1 gigabyte of free space to not enough free space. And this is when you would get an email telling you, something has changed, please update your settings. Yes.
So isn't it really the case that for a lot of users what they want to do is just to say, take enough space resource from me to make it the case that anything I ask you to back up that you have backed up?
Yeah. So
you don't want to play with this at all.
Right. So you actually have that. So actually, in the paper, we mentioned that it would be very easy to implement exactly that. You could have just a little checkbox, or you could even check that at install time. Whenever I always want 5 gigabytes of free space, I always want to be able to back up stuff. Just keep increasing my supply so that I'm always fine. That would be an easy feature to implement. We didn't take care of that in the prototype. Yes.
Isn't there a transaction cost involved? Because if I give you 100 GB of space on my disk and you have stored some files, and I keep on changing that space every day, then you will have to use bandwidth in order to store new files and then delete them, and store new files and delete them. So there's a big transaction cost involved. So probably the users which maintain their, or like in banks do, right? If you are a fixed rate deal for a long period of time, then you get a better return to your investment.
Yes. So it's not the idea that the user keeps moving the slider to the left, to the right, to the left, to the right every day. The idea is that the user sets this at a level once and then essentially leaves that at this point.
But
and then
so the question is, what are the incentives for the user to do this behavior, to follow this behavior? Like at the moment, I've not heard anything which stops the user from changing his markings every day or every minute, in fact.
Yeah. Well, the user, the idea is that the user has a cost for changing this every minute, and then he doesn't actually gain a lot by doing this. Excuse me. So if the user is currently, essentially think about why would the user make an instantaneous change to this and then change it back 5 minutes later? If he doesn't want his computer bandwidth or storage be used for the next hour because he's doing something very important, he could just put the application to sleep. Nothing prevents the user from shutting down the application, then we can't access his device. The idea is that the user sets sliders in such a way that he will be fine for the next month or so, or whenever he reaches his limit on the left side, and then he will open it again, and then to slightly adjust the sliders. That is kind of the idea behind this. Okay. So let me get back to my presentation. Okay, so now that you've seen the interface to the market, let me talk about the theoretical properties that we obtain from this particular design. So remember that efficiency required that we can allow the users to supply the resource ratios supply the resources in different ratios. And the resulting problem from this freedom that we're giving users is that we now have a concern about the safety buffer between the current demand of the system and the maximum supply. And the only tool to our disposal is the price vector P that we use that we can update over time depending on aggregate demand and supply to achieve the desired buffer in our system. So let me illustrate this problem. If this is the current demand in arbitrary units for space, upload and download bandwidth, and this is the current maximum supply that the users are specifying with these sliders. then we can see that we have a very large buffer on space and download bandwidth, but a very small buffer on upload bandwidth. So we are relatively unsafe here. If we have a little bit of variability on the user's demand side, we might run out of upload bandwidth very quickly. So we want to increase this buffer and decrease these two buffers in return. And we'll say that a system is maximally safe if we maximize the relative buffers across all three resources. And this is assuming that the variation on the demand side for the three resources is the same, and we don't have any additional knowledge about that. So to make this safety property more formal, let me define what I mean by a buffer size. So the size of the buffer between maximum supply and current demand for a particular resource K is simply the ratio of the maximum supply and the current demand for that resource. And then the overall buffer in the market is simply the min across all individual buffers. Okay. And then I'm going to define this notion of a buffer equilibrium, which is a price vector P and a maximum supply vector supply P and the current demand vector little demand P, such that the buffers for space, upload, and download bandwidth are the same. So the buffers are, the relative buffers are the same as I've shown you in this picture. And then we show in the paper that if the buffer equilibrium is unique, which it is under certain natural assumptions, and given that buffers are growth substitutes, which essentially means that user supply and demand reacts to price changes in a natural way, then the size of the buffer is maximized in the buffer equilibrium. So we show that if we find a price vector such that the relative buffers are the same, then we've maximized the buffer size in the whole system and essentially maximized the safety property of the system. So now that we know that this is a desirable state of the system to update prices, let's ask the question, well, does this price vector even exist? And under what conditions does it exist? And to answer this question, I'm going to define what I call admissible user preferences, where we say that a user's preferences are admissible if they're continuous, strictly convex, monotone with respect to the services they're consuming, and strongly monotone with respect to the supply resources they're supplying. And here I'm making this distinction. Normally, economists, to show equilibrium existence, would assume that preferences are strongly monotone with respect to all commodities in the market. But we are making this distinction because we don't think that strongly monotone preferences are realistic with respect to service products. What this means is if strongly monotone preferences would mean that here on the supply side, it means if I let you keep 1 more megabyte of your space, you're strictly happier. If I let you keep 1 more kilobyte per second of upload bandwidth, you're strictly happier. So this makes sense to assume strongly monotone preferences here. For the services, however, that doesn't make sense because if I let you back up 1 more file, but I don't let you retrieve that file or store that file, then that's useless to you. So we have these strong complementarities on the demand side between the different services that you're consuming. Only if I let you back up 1 more file, store that file, and also retrieve that file at some point, you will be happier. But not with respect to every individual service.
You might be strongly monotone with respect to a bundle of services.
Right. You would have, yes. So essentially but not with respect to individual services.
Right.
Which turns out to be important for the theoretical analysis of the equilibrium. So given that all users have these admissible preferences, we then show that a buffer equilibrium is guaranteed to exist in our market. And the proof is pretty technical involved, and I just want to give you a brief sketch to give you an idea how we get to this result. So we define this function zk of p, which denotes the relative size of a buffer on a particular resource k compared to the average on all resources. And then we show that given that users have admissible preferences, if we decrease the price of this resource k to 0 and keep the other prices constant, then at some point there will be a resource L whose buffer will be larger than the buffer for resource k. So this is assuming that if users have these admissible preferences, they are reacting to price changes in a reasonable way. So equipped with this lemma, we can then let delta denote the space of all price vectors, and then we construct a fixed point correspondence f from delta into itself. We prove that f is convex valued and upper hemi-continuous. Then we use some heavy machinery, namely Kakutani's fixed point theorem, to prove that such a fixed point always exists. And then we prove that each of these fixed points constitutes a buffer equilibrium. And then we're done showing that a buffer equilibrium always exists with these admissible preferences.
Isn't the lemma immediate? After all, if the price is zero, the supply is going to be zero. If you pay me zero for my disk, I'm going to give you none. So Zi is going to be bigger than ZKP.
Yeah, it's not immediate if because what you need is that users. So first of all, we can never price vectors equal to zero leads to undefined user preference. So as we let the prices go towards zero, but what you need for that is that users have these admissible preferences so that they react to price changes in a reasonable way. And you need exactly all of these conditions to guarantee that users are reacting to price changes in this way. And why? So you might think this is obvious, but this is essentially characterizing exactly what kind of conditions we need to get this. And perhaps more interesting is then the next result, which is exactly when we relate some of these conditions. So now the previous result assumed that all our users are rational, in particular that they have these strictly convex preferences and strongly monotone with respect to the supply resources. However, these characterizations might be violated in practice. And so users might be called irrational because they might not update their settings immediately. So this means we are changing the price, but they're not updating their settings, so they're not satisfying these assumptions. They might be price insensitive. I mean, they might update their settings, but they might not set them correctly according to the current price vector. Or they might be adversarial, trying to simply harm the system or bring the system out of equilibrium. So I was interested in analyzing the robustness of the equilibrium to this kind of adversarial user behavior. And calling it adversarial from here on is essentially assuming that the users are updating their settings in the worst possible way for the existence of an equilibrium. So it's incorporating all of these. And it turns out that the robustness of the equilibrium depends a lot on the degree of freedom that we're giving the users. So the degree of freedom is, I'll define this parameter gamma, which denotes this degree of freedom in the following way. We let each user have a ratio of supply for resource A to supply for resource L, which is different up to a factor of gamma to the system-wide ratio of resource K and resource L. So this is essentially saying how much wiggle room am I giving my user in moving the slider to the left and to the right before the user is hitting one of these boundaries. So if gamma is equal to 1, each user has to provide the resources in the exact same ratio as the system-wide demand for that resource, so I couldn't move my slider to any side before hitting one of the boundaries. And when gamma is larger than 1, I give the user this freedom. So the larger gamma, the more freedom I'm giving my user.
When you say system-wide demand, you mean instantaneously? Just
I mean
the current demand?
Yeah, it's a current demand or average over the last 50 days or however you want to measure it. Yeah, I think we implemented this as a weighted average over the last 100 days or something. 10 minutes left? Okay. So now that we've specified this freedom, we have this theorem showing when does the equilibrium exist with adversarial behavior. And we show that if the demand by the rational users is larger than gamma squared plus gamma times the demand by the adversarial consumers, and if the rational users still satisfy these preference assumptions that we called admissible before, then a buffer equilibrium is still guaranteed to exist. So I really like this theoretical result because it gives an immediate market design implication for the operator of this market. It essentially says the less freedom I'm giving my users, so the smaller I choose this gamma, the more robust I will be against, the equilibrium will be against any kind of adversarial or irrational behavior. So to to visualize this a little bit, what this theorem essentially means is it's easier to see on this graph. Here on the x-axis, I'm plotting the demand by the adversarial users divided by the total demand in the system. So essentially this is saying if only a few of my users are adversarial or irrational, then I can set my gamma relatively high to something like 5, and I'm still guaranteed that the equilibrium is guaranteed to exist, so I can reach the buffer equilibrium and be safe. As I'm increasing the number of adversarial users, or actually increasing the demand that comes from the adversarial users, I have to decrease my gamma, so I have to decrease the freedom I'm giving my users if I still want to guarantee that the equilibrium is guaranteed to exist. Okay. So the last point I want to show you is, so now that we've seen the theoretical properties of the market, I want to briefly show you a user study that we did to answer the question whether the user interface is actually a usable instantiation of the hidden markets paradigm. And we did this study with 16 users, 8 female and 8 male, no UI design experts and a mix of experts and novices. And we gave each user 11 tasks which consisted of different scenarios with increasing complexity that they had to go through. So a task could be something like, please change the settings such that you have approximately 20 gigabytes of free online backup space, but you're not allowed to give up more than 70 gigabytes of your own disk space. So that's a very easy task. More complicated tasks could have combinatorial constraints telling you that you don't care about your upload or download bandwidth, but you want to minimize the amount of hard disk space you give up. So increasing complexity. And then we essentially measured, or we observed in how far we achieved this invocation of the right mental model in the user when he was interacting with the system, and whether the user still took the right action influencing the underlying market. And this is a very, very condensed overview of our results. And this is partly answering your question about the peer-to-peer backup system from the beginning. So the first mental model is give and take, which means do the users understand that the more resources they are willing to give up, the more they will get in return. And based on our user study, we find that when interacting with this UI, all users eventually understand this, that if they want more, they have to give more. As we see that as the complexity of the task got more complicated, certainly less and less, fewer and fewer users fully understood or correctly solved the task. So the second mental model that we tested was the bundling of the resources. Do they fully understand the complementarities of the system? And here we had a success rate of 9 out of 16. And then the pricing aspect was the most difficult to understand, meaning that the users, found the optimal setting for their sliders given the current scenario and the current price vector in the market. So I want to briefly summarize the results from this project. And the thing I want to point out again is that a crucial element was that we designed the user interface and the market simultaneously. And many of the design features only make sense if you think about the interaction of the two, and only then do you actually see why this works and what the value of these design features was. So on the left side, we designed a system which allows the user to interact with the market despite having a low frequency of interaction. We hid the bundling aspect of the different resources. We hid the account balances and the payments from the users. And the pricing was kind of semi-hidden by allowing the users to experience the pricing when playing with the sliders. The last aspect is, was there even a market at all? And so when I asked the users at the end of the user study, well, what do you think, what kind of system did you just interact with? What did this remind you? None of them actually said or had understood that they just interacted with the market, which I actually think of a nice design feature, because I didn't want to evoke this mental model of interacting with the market with monetary constraints and so on. So the market worked without the users knowing that there was a market. On this side, we designed the market in such a way that the account balances balance over time automatically if the users are online long enough. We introduced this buffer equilibrium concept and showed the degree of robustness towards adversaries depends on the degree of freedom that we give our users. And we designed this very simple pricing mechanism which leads to this linear interaction for the users. Okay. So now I have 3 slides left on an overview of some of my other research. How much time do you have left? couple minutes? Okay, I'll spend a minute on each of the projects, and yeah, feel free to ask me more details about these projects in later interviews, or if we chat later in the day, today or tomorrow. So some of my other projects I worked on is, this was an experiment I ran in a peer-to-peer network on the degree of selfishness and altruism, where we asked the question, why do people contribute in peer-to-peer file sharing networks if they don't have to? And the methodology here was that we did an online field experiment with more than 10,000 users, where we released a file sharing client in 2 versions, one altruistic and selfish, and then we observed users' behavior, and we had some survey responses from users. And then we performed a regression analysis to find the most predictive factors for users' degrees of selfishness. And the main finding here is, which I'm most excited about, is that understanding the underlying public goods game of the peer-to-peer file sharing system significantly increased the likelihood of being altruistic, in particular by about 15 percentage points in our experiment. And we found that 20% of the population can be moved from being altruistic to being selfish if we increase the personal incentive that we give them for downloading the selfish client. And then we found lots of other correlations that are also interesting, related to country, operating system, age, and so on. Another project I worked on is what I call work accounting mechanisms, where the setting we consider is a distributed work setting or system, where you can think of file sharing or ad hoc routing networks where users are consuming work from each other and performing work for each other, where there's no center such that no monitoring is possible, and agents have to rely on each other's reports about how good or how bad an agent in this system is. And the question was, how can we make truthful reporting to each other about the work you received and you've performed incentive compatible? And the main result that we provide in the paper is this mechanism called drop edge, which drops some part of the information available to the agents depending on the current context, but making it, but then thereby also removing any kinds of incentives for misreporting to each other. We also have a negative result that we show that there's no useful, where useful is defined in a technically meaningful way, Sybil-proof work accounting mechanism in this domain, where Sybil-proof means that if you consider attacks from multiple agents on the system, then there's no useful system that is robust to all of these attacks.
Are these technical results, or are these, you've looked at users and this is what makes them
No,
behave in the best way?
The first two is a theoretical.
Okay.
Yeah, it's technical results. This is not involving any real users, in contrast to the previous study. The last aspect is we also perform simulations with, not with real users, but with simulations, evaluating different allocation policies in these distributed work systems. Okay. And the last project I worked on that I just started last summer, also at Microsoft Research actually, and this is also kind of part of my research agenda that I want to work on moving forward, is this question of how to design market user interfaces that make economic decisions easier and more efficient for users based on a behavioral user model. So we studied this particular market of bandwidth allocation on a smartphone, and we asked, and we did a lab experiment with 53 users obtaining about 15,000 click data points, and we tested different ways that we can change this user interface, and we evaluated what the impact of changes to the UI is on the market efficiency or market performance. And so we performed a regression analysis again, and we found that giving users more choices in what they can do on this market first increases the market's efficiency, but ultimately it stagnates or even slightly decreases overall efficiency. And then we found lots of other behavioral effects that including a large degree of loss aversion. Users are overspending their budget continuously, and they're very impatient when they are losing value. But we can also talk more about these projects offline if you want to later. So now I want to conclude. I showed you this new paradigm of hidden market design, and I illustrated this using this peer-to-peer backup application, and I showed you how we hid many of the market's complexities from the users while still enabling an efficient resource allocation market. The user study that we performed shows lots of promise for this paradigm, although it also alluded to very interesting questions at the intersection of user interface design and market design, which there's still many open research questions which I think are very important to answer in the future. So other future work I want to work on is extending this or applying this hidden market idea to other domains. One that I'm particularly excited about is the smart grid domain, the future of power and electricity networks. And then I also want to do more experimental and theoretical work studying these market user interface design questions. Okay, thank you very much.
Thank you for a very fascinating talk. I think